אנחנו... אז אני אעבור לעברית ל5 דקות. גם הוא? לא. באנגלית. אוקיי, English. We have in the next session we have four talks by לכבוד, יאיר, אחרי, and 20 minutes and I'm trying to 20 minutes. Difficult to do that. We have the title there, so I'm going to read it.
So, good afternoon, everybody. I'm happy to be here today to celebrate with Aaron's 85th birthday. The study that I'm going to present here today is part of an ongoing PhD thesis by Matan Ben-Asher, which is conducted at Ben-Gurion University, in conjunction with On Kuvi from the Geological Survey of Israel and Josh Warren from the University of Oregon. We live in a carbonate land. Okay, so we live in a carbonate land, and actually, when we look at the distribution of carbonate landforms around the world, they are quite ubiquitous. But despite this widespread distribution, the amount of studies which focus specifically on carbonate landforms over the last 10 or 20 years is relatively low in comparison to studies which focus on silicates. So what we're going to do today is to try and put a small spotlight on carbonate landforms and how we think they evolve. As early as 100 years ago, this gentleman, J.K. Gilbert, realized that soil-covered hill slopes around the world tend to be convex. And Gilbert explained this observation as being a result of soil creep. And he reasoned that the flux of weathered material, which we can call weathered rock or soil or regolith, the flux of weathered material must increase as a function of the distance from the divide under steady state condition. So the flux in point A must be higher than the flux in point B, and the flux in point B must be even higher. And to accommodate the increase in flux, the slope must increase. The hill slope gradient must increase, and therefore the hill slope is for the hilltop is convex. Now, the range of processes which give rise to creep includes both biogenic mechanisms such as burrowing of animals, tree throw, food tread, and physical mechanisms such as wetting and drying cycles, freezing and thawing, and rain smash. Actually, Aaron Ya'ir was one of the pioneers focusing on burrowing activity and emphasizing the potential significance of burrowing in creating sediment hill along hill slopes. Nowadays, it became very popular. Now, almost 60 years following Gilbert qualitative observation, it was formulated, his observations were formulated in a quantitative manner, and the idea is that if we have a steady state hill slope morphology with a steady soil or regolith thickness, we can look at the rate of lowering of the hill slope in a mass balance sense using a continuity equation, and the rate of lowering of the hilltop will simply be the difference between the flux out and the flux in. Now we can formulate a transport law based on laboratory experiment and empirical observations, which relates the flux to the slope. The flux is a linear function of the slope, and then take this flux and plug it into the continuity equation, and what we eventually get is an equation which is identical to what we all know as the diffusion equation. It's mostly familiar as the heat diffusion equation, but what we have here is diffusion of elevation. Now, what this equation predicts under steady state condition is that steady state hill slope, which are evolving by creep mechanism, should have a parabolic form. They should follow a parabola formula, just like we see over here, which means that the gradient should increase linearly as a function of the distance from the divide. And the curvature of such hill slopes should simply be the ratio between the lowering rate of the hill slope and K, which is the diffusion coefficient. Okay. Now the question is this at all relevant to carbonate landforms? And what we wanna see is we wanna examine climatic effects on the morphology of carbonate landforms, and by climatic effects I mean to examine both how the mean annual precipitation influence the morphology, microclimate in terms of slope aspects, and also things which are related to climate, such as dust flux, and to see what we can say about the mechanisms which are active on carbonate hill slopes, and to try and constrain the relative magnitude of chemical weathering relative to physical erosion. Now, I'm going to raise more questions today than provide answer, but hopefully we will be able, as we get more data, to answer most or some of these questions. So our study sites are located at the eastern Mediterranean along dominant climatic gradient from around 300 millimeters per year of rainfall in the south, semi-arid region, to 900 or 1,000 millimeters per year in the north. Co-varying with this gradient, we also have a gradient in dust deposition. So you can see here contours of dust fall, current dust fall, and you can see that or you can imagine that the numbers decrease as we go to the north. Okay, so for most of these sites, we have an airborne LiDAR which depicts the topography in this site, and this is what we see when we analyze the high-resolution topographic data from these areas. So what we can see here is that the profile of the hill slopes are often convex and exactly parabolic in form. So I'm not sure you can see the gray line over here, but this gray line is exactly an equation of the parabola, and you can see that up to a certain distance from the divide, it matches the hill slope profile perfectly well. Beneath the hill slope profile, you can see how the gradient behaves as a function of the distance from the divide, and see that it increases linearly as a function of the distance from the divide, just like we would expect if those hill slopes were controlled by soil creep. Okay, but we suspect or we hypothesize that some elements should be different when we think about our carbonate hill slopes, and the two major parameters which should vary here. One is that we expect the magnitude of chemical weathering to be higher than in silicate rocks, because carbonate rocks dissolve more readily. So we need to introduce this term into the equations we've seen before. And we also know that there is dust flux over these hilltops. So the soil or the mobile regolith that we have is not only weathered rock, but is also gaining a non-autogenic component from the air. So we need to take this parameter into account as well. And this is what we did over here. And basically the prediction here is that if the magnitude of the relative chemical weathering is high, we can lower the hilltops at the same rate, but with a lower curvature, with lower gradients and lower curvature. If we have significant dust fall, we need to mobilize not only the weathered rock, but also the dust, and therefore to get the same erosion rate, we need to increase the gradient or increase the curvature of the hilltop and get a hilltop which looks more like this rather than like this. Okay, so how is the curvature around our study site really looks like? So what we see here is the hilltop curvature as a function of the mean annual precipitation, and we can see that there is a trend in the data. The curvature is high at low mean annual precipitation. It then decreases and then increases once again. And we need to think how different parameters could influence such a behavior. So we already know, or we already suspect that the dust fall decreases as we go north, and it decreases, and it means since it co-varies with the rainfall, it means that the dust fall decreases as the rainfall increases. Okay, so as we go from here, from the southern part of Israel, and the rainfall increases, the dust fall decreases. And what we said earlier, when the dust fall decreases, we can actually do the same amount of erosion with lower slopes and lower curvature. Okay, so we actually decrease this parameter over here, the production of dust, P dust, and by decreasing it, we can decrease the curvature. So one parameter which could explain this decrease is the decrease in the dust fall as we go north. This, however, cannot explain what we're seeing here. Another parameter which could account for this decrease is the magnitude of chemical weathering. If the magnitude of chemical weathering, again, relative to physical weathering, increases as the rainfall increases, which makes sense, the magnitude of chemical weathering at 500 millimeters or 400 millimeters should be higher than in 200 millimeters, then goes towards 1, and again the curvature decreases. So the relative magnitude of chemical weathering again can explain this trend, but not the increase that we are seeing over here. Now we have to think of 2 more parameters. We have too many free variables here. 2 more parameters. One is the regolith production rate, the rate at which the bedrock is converted to soil, and the other one is how does the diffusion coefficient vary as we vary the precipitation. So let's first look at the regolith production rate, and a good proxy for the regolith production rate can be obtained from cosmogenically derived erosion rate, and we have an extensive data set in the Eastern Mediterranean by Uri, by Shaked Avni, and by myself, and work which was conducted mostly at Aaron under Aaron Matmun's lab. And what we can see here is that as the mean annual precipitation increases, the erosion rates, or we can look at the erosion rate as a proxy for the regolith production rate, they increase consistently. And if we look at theoretical dissolution curves as a function of the partial pressure of carbon dioxide, we can see that theoretical dissolution curve do not exactly follow this line, but they mimic this trend, and they can explain part of the variability in the erosion rate that we see over here. The bottom line here is that we do not expect this parameter to the regolith production rate. We do not expect it to go down as the precipitation increases. Okay, so let's now move to the last parameter that we want to explore. Or you know what? Before we move to this parameter, we wanna look at the relative magnitude of the contribution by the dust and the magnitude of chemical weathering as a function of precipitation. So what we did here is we excavated pits at the hilltops and at the bottom of the hilltops, and we were very careful to collect all the material that we extracted, that was extracted from pits, and characterize this material. And so first, what we see is that the soil depth is relatively shallow, in between 10 to 50 centimeters. There are no distinct horizons within this soil, and for us it was a surprising observation when we weigh the weight of carbonate clasts that were extracted from these pits. What we get is that the fraction of carbonate clasts within the pits is very large. It's more than 30% of the weight of the material within these pits. Okay? What it suggests, or what it immediately implies, is that at least 30% of the material in the pits is autogenic. It did not come from the dust. It was not mobilized in the air. It's a weathered rock. Okay, at least 30% of the material that we see over these hilltops, and probably much more. Now, we also see that when we look at the fine fraction, and this was demonstrated by Rivka Amit, by Yuda, and by Aaron in many studies, that when you look at the fine fraction, the non-carbonate fraction of the fine material, then the particle size distribution of the fine fraction basically resembles what we see in the lost deposits in the Negev, and the trend that we see is a decrease in the mode of the grain size as we go north from the lost deposits to Ramot Menashe, which is near Haifa, several tens of kilometers or more than 100 kilometers further to the north. So we have clear indication, which is not surprising, that there's also a significant contribution of Aeolian material overtopping these hilltops. Okay, but we want to find a quantitative way to put a number on the contribution of the Aeolian flux. And in order to do this, what we actually need is we need two immobile elements, like, for example, aluminum and zirconium, or aluminum and titanium, provided that we can convince ourselves that these elements are indeed immobile. And by looking at the ratios of these elements in the soil, the rock, and the dust, we can pinpoint, or we are open to pinpoint the fraction of the dust in the regolith. Unfortunately, we are not there yet. There were several problems with getting the numbers for this kind of calculation. But what we have for now is a trend just for the aluminum oxide in the soil, dust, and the rock. And we can see that at least that some specific pits in some settings, the percentage of aluminum oxides in the soils are significantly higher, not only from the bedrock, which is long known, it's also significantly higher from the dust, from all the data that we have on the dust itself, which means that to get, for example, near Jerusalem, 14% of aluminum oxide within the fine fraction of the regolith, you need to lose at least 50% of to dissolve at least 50% of the dust material. This is assuming that all the fine material is from the dust and not from the rocks. If part of it is from the rock, you need to dissolve more. So at some settings, we have indications for minimum loss by chemical weathering, which is 50%. We hope that in the near future we will get more precise numbers here. Okay, how many minutes are there? One. Okay, so to constrain the diffusion coefficient, unfortunately, we could not constrain it within the carbonate landforms themselves. So we went to a setting where we have cinder cones. We know the age of the cinder cones. We know their initial yield slope gradient by the tip of the layers, and we modeled these yield slopes, and we got numbers for the variance in the diffusion coefficient as a function of precipitation. And you can see here that the diffusion coefficient decreases with precipitation, at least over the range from 600 millimeters per year to 1,000 millimeters per year. The diffusion coefficient is also lower at north aspects relative to south aspects. Now, we think that the reason for this decrease is simply the vegetation density. What we see here is a very clear pattern using the NDVI remote sensing index, that as the precipitation increases, the density of vegetation increases, and north aspects have more dense vegetation than south aspects. And what we think is that what the vegetation does, it introduces root strength cohesion into the soil, into the regolith, and this root strength cohesion inhibits transport. So it decreases the diffusion coefficient and triggers asymmetry in the hill slopes that we observe. North aspects are steeper than south aspects, and we see this trend not only in the cinder cones themselves, but also in carbonate hill slopes adjacent to this area and further away from this area. Clear asymmetry in the hill slope gradient. North aspect are steeper than south aspect, and they are more vegetated. Okay. Last slide. So we are back to our diagram of how the curvature varies as a function of precipitation, and we put next to it now our diagram with the diffusion coefficient, and we add to this diagram several points from modeling of cinder cones in the southwest US. Unfortunately, we don't have cinder cones in our area which experience 100 millimeters per year and 200 millimeters per year. And what we get here is an apparent pattern where the diffusivity shows a maximum at a certain precipitation around maybe in between 400 to 600 millimeters per year. And actually such a pattern, just flip it over, could explain the trend that we are seeing over here. I'll just end with this diagram, which goes back to Tom Dunn's paper of rain splash effect. So this is a theoretical consideration of how one of the mechanisms which can create creep is influenced by vegetation and by mean annual rainfall, and the prediction is that it would be a function with a maximum. The diffusivity, which is strictly due to rain splash. Surprisingly enough, the magnitude of precipitation that occurs in is very similar to what we see over here. Okay, I'm over time, so I won't go through the conclusion, and thank you for listening.
Okay, you don't need to be here. Okay, you have different scale, stream capturing, and other products in the market.
Okay. I want to take you a short dive into a very known in one hand and complex in the other hand, the relations between stream capturing and the neotectonics. I'm sure that Aaron knows very well these issues because the master thesis and PhD thesis of Aaron were done in the eastern part of the Galilee. And of course, Nathan Shon and Nathan Tabor and Nathan Sasra, all of them have the same complex relations between some reorientation or changing or evolution of the systems, and of course, neotectonics related to the Rift Valley. In the Galilee, in the case of Aaron, and I will take you south into the Negev area. Only to refresh our minds, this issue, of course, is very widely already studied. And the common knowledge that everybody knows is that we can start with a kind of situation like that we have a major stream flowing or moving in the area from one point to another one, and there's another one, a small one, that is coming from the side, and it's expected that this little one is supposed to hit somewhere in this basin, and of course make a kind of capture and take, of course, the whole flow into the small basin, relatively small. And there are some even maps that can say something about this orientation of the streams. First of all, leading to that direction in the border between Ohio and Indiana, and then move all the way back into Lake Erie. Now, that's the common knowledge, and when I was a student for Aaron, we learned from him that it's a problem, major problem with that, because in water divides, usually there's not enough energy to make a kind of a backward erosion in water divides. And what Aaron told us is there's a zone of no erosion that was supposed to occur somewhere in the slopes, both sides of the water divide. And then, of course, there's no way how to make capture involving headward erosion, because there's no way how to overcome the water divide that is zero energy, almost zero energy. Everybody knows that, also Aaron, of course, slow processes can maybe make some change in this view, but they're supposed to be very, very, very slow and not so common. Now, on the other hand, however, in the Negev area, we have a lot of evidences for river capturing. And this is only a part list of all these places where people were reporting about a change of drainage orientation or change of capturing processes. The well-known is the Tzin, of course, but Chemar, Tzafit, Chatira, the Lots, the Paran that I will present lately, Sagi and others, even in the south, the Gishron, the relation with Nahal Shlomo, all these were reported as stream capturing. So what's going on? If there's a limitation to make this process, so how come they're so, you can find it almost everywhere. Now, I will go a bit into these issues by taking some arguments that will help us to understand the drainage evolution. Because if you understand the drainage evolution, you can maybe say something about capturing of some of the rivers by the others. And I'm using this sketch coming from my PhD of the Arava Formation. The Arava Formation is a key unit widely distributed in the Negev, started about 3.5 million and go all the way up with 2 members. And we had also the Tzricha Formation. The names are not important, but there are key units that you can follow in quite a wide area in the drainage basins of the Negev, and then of course follow their evolution. Now, if you do it carefully in a PhD time, you can come out with a kind of a map. And this is a wide distributed map from Elat region in the south into the Dead Sea in the north almost, covering the majority of the Negev in some part of Sinai. And this is orientation map. This is gradient map. Orientation of the regions leading from high area over here to the downstream areas, low lands in the Dead Sea, and each one of these dark lines indicating the gradient that you can even measure what was the original gradient of the flow system during the Pliocene time. We are going back 2 million years ago to the early Pleistocene, and of course if you now want to trace the formation or change or capturing, you have a kind of baseline of units that can help you. Only to say that since then, you saw that the integral drainage basin of the Nekarot Paran Basin, the large one that existed during the early Pleistocene, today is of course totally disintegration of this system into parts, maybe by stream capture, and we are having a phase of fragmentation of the large basins into small ones, maybe by drainage capture. And of course, we follow a bit this understanding that something is going on here by changing the drainage basins by following 3 case studies. That would be the major one, Anaka, that is located south of Machte Shamon. This is the crater of the Ramon. Of course, we are located on the edge of the major Dead Sea transform, the major tectonic element in the region here. Then we very briefly say something about the sea that everybody knows, because that was the key capture site in the Negev, and then of course very briefly also about the Paran that I studied during my PhD. Now, what's going on? So, first of all, we have of course some tectonic lines to consider. Beside the transform, we have these Sinford, Ramon, and Arif, and all these names. Maybe there's some neotectonics going on that will explain a bit of this fragmentation of the drainage system and the change for one another. Maybe they are also involved in stream capturing. But we start with one that has nothing to do with local tectonics. No fault line, nothing that we can relate that is directly related to tectonics. We have this line moving all around by the line, the dark line, the black one. This is the meandering pattern of Nahal Anaka during the time of the Arava formation, about 2 million years ago. And you can see from the headword over here, he has meander number 1, meander number 2, and meander number 3, making kind of a very, very long and curved coast. And it was replaced by a very sharp and very straight one, the blue line, that actually capture all these meanders. Now we pay attention to these meanders to see what's the mechanism of capturing or cutting meanders. By a stream, you can see this stream, that is our day's Anaka stream, that is cutting meander number 2, and then meander number 1, and the midpoint, or a dry waterfall of about 40 to 50 meters is located up over here. And now the question is, how come this small one, or relatively small, is the same Anaka, but anyhow managed to cross the water divide that was first located here, just in the meander part, and then, of course, doing quite recently, because it's very close to the meander neck, in the last years, in the last 1,000 years. So we get a closer look on this environment. On one hand, the meander is moving to 700 meters from this spot, right to the north, and then coming back over here. And you have the midpoint, about 40 to 50 meters. And you have all this configuration, starting with geology, the formations, the ora and profits from the Turonian time, and sedimentation of the Q3 unit. That is very important. The Q3 unit is the term that we're using, mapping alluvial units in the Negev, and this is the last ice age sediments, like the less. In this case, there are gravels incorporated with less. And they are quite high, I mean, quite thick. It's about 6 to 8 meters thick of section, alluvial section, just deposited very close to the neck or to the water divide that was local water divide in this case, that was of course making the meander. Now, a very close look on the neck will give you some insights about what's going on here. This is the level, this is the midpoint of today. The sedimentation was occurring over here, and the water divide was made of a part of sludge. A very, as you can see, this bedding, tilted bedding because of the slide. This area is made of clays, fragments of limestone, very reduced section, and very thin because of the meander neck. Now, of course, if you think about, that would be a kind of a key point in order to make the change, because it's very narrow, it's lower in topography, and the position of this unit above and very close to the water divide maybe have something to do with this process. We believe that the major flood running from the Anaka went down and made the breaching of the water divide, and the process, of course, is the upper stream into the lower one, and not the reverse way like we saw in the previous example. Now, very briefly about the others. Nahal Sin, everybody is aware of that. The Boker, very close to the site, a whole site of long-term geomorphological studies in the Boker. This is a kind of incision to a depth of about 120 meters because of capturing that occurred in the Boker. And to sum up, a study that I made with Silverman, we think that was 3 stages. Here's the original stage in the Pliocene time. The position of the Arava formation in this case is a variant of the Arava formation, not so important. A kind of a tilt that was imposed on the region here along the Tsin fault, made the orientation of the flow of the major Tsin valley and the upper Tsin, we call it, to shift to the east and overcome a reduced elevated water divide over here on the Turkiya formation that is very soft made of clays, another key unit in the region that is very sensitive to geomorphological change. And the outcome of that, of course, is reorientation, total reorientation of the whole system. Again, the major force is the Tsin itself. He's not waiting to anybody else to take him. He's doing the job, he's doing the work. Another example for that, from other place, the Paran. Now we're located about 100 kilometers to the south of Stevoker. This is the gorge of the Paran, the bottleneck of the Paran, flow direction is indicated. The Arava Valley is to the east. Above the channel, again about 100 and a bit more meters above the channel, you have these remains of NA is the Arava formation from the Nergen, from the Pliocene time. And so we have a common channel just above what is today the nowadays channel leading to the Arava, and previously there was a channel leading to opposite direction. You have the numbers for the topography elevation, and you have the reconstruction of the channel. The channel was coming from the Merezes Menucha, one of the hills bounding the Arava, and moving all the way from east to west to join the major stream of the Paran, that was located, of course, to the west of this location. Later on, something happened, and the whole system was reversed, and the channel was used by the our days Paran in order to move all the way into the Arava. You have the fault line of the Paran, you have several other lines of faults involved, yes or no, in the process. But anyhow, this is a kind of reversal of the drainage system. And we think that the story is like that. Again, an original shape during the Pliocene time, Arava formation was involved again as a unit that is the topographical elevation in this basin. And then, during the early Pleistocene, we have dates on that, we moved like that as a tilt of the whole region to the east toward the Arava. Some faults, not the Paran fault itself, but the others, the Barak, the Tzvicha faults, those that are elongated to the north, parallel almost to the transform, were active, and then the whole area was sliding in a way to the east and shifting the whole drainage system, and of course excavating also the Paran bottleneck. Now, if you sum up the whole thing, we know that the whole eastern Negev is tilted to the east. This is the eastern Negev. This is the line of one of these tributaries of the Paran, and this is our day's topography, and that is assumed gradients of the Palo River that was existed during the last 2 million years ago. That was the gradients. Of course, we cannot have any clear indication of the precise gradients, so we gave some kind of several hypothetical possible gradients, and we know that the Arava is already subsided in the last million years by 700 meters, or between 450 and 700. This is quite a lot, and this of course totally influenced the whole picture. Now, this is the summer coming from my PhD. The Tzin case, the Paran case, and the Anaka case, all of them are simply because eastern tilt of the Negev. That one is shifted to the east in the Tzin area in order to meet the lower part of Nahal Tzin and make this sharp curve in the orientation of Nahal Tzin. That one is the increasing of the gradient as much as we go in Anaka, and the last one is reversal because of the same thing, collapsing of the Arava down, pushing all the eastern part of the Negev toward the Arava, and of course change the whole orientation of the flow. That's almost the last one. Only to say that if you take now the time starting in the Miocene, 10 million years ago, and that's almost present. And on the other hand, you have the tectonic plates. We are starting 10 million years ago with the creation of the major drainage systems in the Negev. Just after the major uplift was following the major development of the Rift Valley, of the Dead Sea Rift Valley. Later on, there is a time of incision that is required in order to deposit the Arava formation after everything is eased and smooth enough in order to make the deposition possible in the drainage basins. But then we have another tectonic event in the early Pleistocene, about 1 million years, 1.5 million years ago, and this is the reason to the reorientation of most of the Negev drainage basins. So actually, we need to say, it's not a simple case of capturing, because the simple case is not simple because of the water divide problem, but if you ease the situation by tilting because of the tectonics, and we have the numbers of tectonics in the time, you can of course make the whole thing much easier. Combination of specific points on the landscape that are sensitive to the change, like units that are very sensitive to erosion, with the position of sedimentary units very close to this reduced water divide, can of course breach the system, adding one of the major floods running down the major system and not the small one. And the most important thing that we're adding here, the one to make the change in orientation of treated basins are not the small ones that are coming with the pistol, taking the capturing and take the prisoner with them to a new way. It's the major one that gets another opportunity to change its course because of tectonics sometimes, or other possible reasons, and he's the one to make the label, geomorphic label that is needed for the process. Thank you very much.
The next talk. Aהרון, the concept of climate and controlling alluvial terrace aggregation and aggregation north-eastern neighborhood.
The complex relations between tectonic activity, climate, and surface processes has been a focus of much study in the past several decades. These relations between deformation, precipitation, incision, aggregation are based for a lot of debate throughout the world at different tectonic and climatic settings. In this talk, I would like to concentrate on these complex relations are expressed by the different arrows going in different directions. And in this talk, I will just emphasize the two thicker arrows, the influence of climate and tectonic activity on surface processes. And I will do this. I'm going to change. Don't change slides. I will do this in the northeastern Negev. This is the DM of Israel, the Mediterranean, the Dead Sea transform, and the northeastern Negev enlarged over here with the study areas that I will present in this white rectangle. The climate is hyper-arid with precipitation that ranges between 15 to 100 millimeters of rain a year, coming down mostly in 2 to 3 events in the winter. On a geological map draped on the DEM, we can see both the lithology and the tectonics of this region. Most of the region is overlain by carbonate rocks of the Judea and the non-focus groups, mostly limestone, dolomites, which we can see over here in green, and the sandstones of the lower Cretaceous Hakila group. The structure is mostly part of the Syrian arc monoclines, where we can see part of these monoclines over here, the Hakila, and I will concentrate on the Chatzera monocline in this area. This structure started developing in the late Turonian into the Stenonian with several episodes of rejuvenation, the last one being in the Pliocene, and is responsible for the present morphology. Of course, as you have said, the major player over here is the Dead Sea, fold, transform, rift, whatever you choose to call it, right outside this map. And in the context of this talk, its major influence is the development of base level, deep, young base level that draws all the rivers into. So this is a Google map of the area I will talk about. You can see the small crater over here, Nahal Safid over here, and the canyons of Tahmas and Paris over here. The data I will show is based on 3 master theses that were completed, well, not completed. One was completed in 2011 by Fuchter, one by Fassi in 2014. The last one, which is in progress by Nago in Nachal Tzafit. So I'll start with the one in the small crater, Mafesh Katan. Work that, as I said, was done by Fuchter in 2011, published. The small crater, you can see it over here, underlain by low cretaceous sandstones, which also form the lower half of the cliffs surrounding the crater, and the upper half is the limestones and dolomites of the Judea group. The crater itself is drained by the Chatzera drainage system, which incises through a series of alluvial terraces, which we can see over here. Let's look closer at these terraces. You can see just an example of some of these terraces. We'll come even closer. That's 1, 2, and 3. The higher terraces, like this one, are covered with a well-mature, developed desert pavement, 100% cover, mature AV or developed AV horizon, and a very thick, blast-free, dusty horizon. The surface itself is smooth, flat. The intermediate terraces, also covered by a mature desert pavement, we can still see remnants or ghosts of big boulders with some remnants of bar and swell morphology. And the lowermost terraces, of course, younger, with a well-preserved bar and swell morphology. There's also desert pavement, but it's not as developed. And although previous studies suggested more than 8 levels of alluvial terraces in the Maktesh, we decided to limit ourselves to 3 groups of terraces, 1, 2, and in this case it was 0, 1, and 2. The mapping shows nearly a symmetrical distribution of terraces around the active drainage system. This is the active Chatzera Thalid, with the younger terraces over here. And the interesting phenomenon over here is the older terraces, in fact, these days form the drainage divides between the sub-drainages within the Maktesh. Dating of these alluvial terraces was done using OSL and cosmogenic nuclide exposure age dating. I won't go into the methods themselves, just show you the results. And the results are clearly interesting. The highest terraces were abandoned about 300,000 years ago. There's a good correlation between OSL and cosmogenic isotope ages, and these are the ages of the top of the oldest terraces. Notice that this age, the age of abandonment, is within resolution the same age as the beginning of accumulation of the next terrace. The next terrace accumulates for about 120,000 years. I'm sure there are unconformities within each terrace, but there's no major concision. So 120,000 years of more or less accumulation, and this terrace was abandoned at about 155,000, 160,000 years, which is exactly the time that the youngest terrace started accumulated up to near about 50,000 years ago, and then was abandoned with concision to the present valley. So we have 3 generations of alluvial terraces at 280 or 300,000, 160, and 50. Each cycle lasted 100 to 120,000 years. As I said, probably included periods of deposition and incision. Notice that over the last 300,000 years, most of the time, there's aggradation of sediment. But incision was extremely rapid, at least within the resolution of dating. We move to the next study, a little to the northeast, the Fassi study and the Tahmas terrace drainage system, which looks about like this. This is the map of the Tahmas terrace drainage system. It crosses the Chatzera drainage system. You can see it over here in a very schematic drawing. It crosses several sub anticlines, and I will concentrate on the terraces that were deposited in the lowermost syncline of the system, which is the Mazal syncline. On the terrace side, in this photo, we can see the higher terraces. They're very smooth, flat, and the lower terraces, which from this distance, it's a little difficult to see the bar and swell morphology, but it is there. This photo doesn't show the T2 terraces, but they are here. The tower itself runs along this course. The entire valley is inside within Senonian and Turonian units of the Mount Scopus and Judea group. On the other side of this small hill, which I will say something about in a second, is the Tahmas Canyon. Nachal Tahmas runs over here with its pronounced terraces. T2, again, which you can see the surface of T2 over here. Very extensive alluvial terraces, and even from this distance, you can see the bar and swell morphology of T3. Again, the mapping shows the distribution of the different terraces. In this case, the drainage divides are not occupied by one of the alluvial terraces, but are run along table mounds composed of Senonian, Menucha, and Meshash table mounds with an exposure age of lower Pleistocene range between 1.1 to 1.8 million years. So the incision and the beginning of the development of these big valleys, not the valleys themselves, is quite old. A few schematic cross-sections, one along the Nachal Terrace shows the relations between these different terraces. In this case, we can see the oldest, highest terrace with one age of about close to 300,000 years, 280,000 years, but this is 4 meters beneath the surface. We don't have ages closer to the surface. T3 is well dated from its contact with bedrock, with the Turonian Netzel Formation, all the way to the top. Again, accumulated from 130 to 20,000 years, 110,000 years of accumulation. I will now go into the very young terraces. On the other side of the divide, the terraces of Nachal Tahmas, the high terrace, the terrace number 1, is just a little older than 300,000 years. Terraces number 2, A and B, were evaluated about 120,000 years. And this age, I will show in a second, is supported also by exposure dating of quartzite boulders exposed at the surface. The age of T3 ranges between 50,000 and 70,000, but the contact with bedrock was not exposed, so it probably started accumulating earlier than 50,000. On terrace T2, we collected samples from 5 quartzite boulders for exposure dating, and using a kind of a simple model that accounts for possible scenarios of how boulders are detached from the slope and are deposited on the terrace, we get a model age of 120,000, 144,000 years, which is identical to the OSL 120,000 years. So also, as we saw in the small crater, the results from Tahmas Terrace indicate 3 main generations of terraces at about 300,000 to 120,000 and 70,000. Each cycle again is 100 to 120. And although the data here is somewhat limited and not as complete as in the Chatzara in the Maftesh, it also suggests rapid incision between one terrace to the next terrace. Going into our last, third example, Nachal Tzafit, work in progress, so there's not much data to show. Nachal Tzafit is the drainage basin is outlined in purple, and here crossing the Chatzara anticline from the Yamin syncline towards the Dead Sea. Very extensive terraces. We can see the older terraces at the top, intermediate terraces in the middle, and of course the lower terraces with the forest cell morphology close to the river itself. On the mapping of the terraces, if we look at cross-section AA, which is this one, with the limited data we have, we can see the high terraces dated to about 250,000 years. The intermediate ones are 125,000, and the lower terrace accumulating starting 66 or 70,000 years ago, up to 35 or 24,000 years, depending on how we interpret the OSL data. So we get to the combination or integration of all the data. This is a somewhat loaded graph. Let me walk you through this. These are the marine isotope stages from 1 to 10. The gray bars are periods of increased speleothem growth taken from the work of Vax in the Negev, suggested, according to Vax, increased precipitation in the Negev. And each row represents the ages of the different sites that we dated. This would be Nahal Chatzera, which is a small crater, Tzafit. There are two Nahal Tachmas and two synclines in the terrace, which I presented, in this case only this syncline. Solid data appears in solid colors. Interpreted data or assumed ages would be in dashed lines, except for the ages themselves, as I show over here. And what we see is the correlation or the non-correlation between the different drainages, although they all flow on the same, or in size, into the same anticline, encounter the same lithology, and experience the same climate and same tectonics. We can see that the preserved record goes back only 300,000 years. Nothing older than 300,000 years. There are three main sedimentary cycles. Each one lasted, as I said, 100 to 120,000 years. Most of the time, these drainages were in the aggradation mode. They accumulated sediment, even though they are at the shoulder of an active rift. This means that in spite of tectonics, there's too much sediment. And we'll try to explain that in a second. Incision between one terrace level to the other was very rapid, and aggradation and degradation occurred both during glacial and interglacial periods. There seems to be no correlation with marine isotope stages, nor with periods of increased speleothem growth, which was suggested to be triggered by more precipitation. This just highlights the importance of drainage-specific characteristics such as drainage area or drainage exponential curve. I would like to dwell a little bit on the first. How much time? 2 minutes. Okay, so that's good because I'm talking nonsense now. On the 300,000 year record. So the preserved data goes back 300,000 years. Let's assume this is our 300,000 years. This would be the elevation of the active stream from 300,000 years ago until today. Because most of the time the systems grade, then in fact the elevation of the active stream increases, and then over a very short time they're incised. They increase and they incise, they increase and they incise. The overall trend is of course lowering of the system, but most of the time they're not lowering, they're going higher. But these periods are extremely intensive. But this period of time is only part of the history of these canyons. This is our 300,000 years. Canyons started developing 3-4 million years ago, when the anticline, when the present topography was formed. And we don't know what happened over here. There's no sedimentary record. So the question is, why is there no sediment older than 300,000 years, which we could use? The common answer is that it was here and it was eroded. probably the right answer too, but I want to offer another process or suggest an additional process that would contribute to this bias. So let's assume a canyon that is incised below some surface. As it incises, it deepens and the slopes lengthen. So as slopes lengthen, and this would be the depth of incision and the slope length times 2, because we have 2 slopes, just assuming hypothetical average gradients for the slopes, and by the time we reach the average depth of the canyon in the northeast Negev, 300 meters, we have slope lengths that are about 1,000 meters. This means that as the canyon incises, there's more slope to generate sediment. The potential for sediment generation increases dramatically. So it would look like this. As time goes on, the incision produces slopes which increase the potential for sediment generation with the fluctuations of climate on top of this consistent increase. So if we take climate, tectonics, and just the simple geometry and put them together, once base level of the Dead Sea is formed, the response of the system in terms of sediment generation potential is extremely rapid at first, and then like every natural system, it relaxes a bit and becomes kind of constant. I'm sure climate is superimposed on top of it. But if we take our slope that increases and lengthens with time, and combine these two, we get a situation like this, which may have some threshold where below it there's not enough sediment to form and maintain terraces, and above it there's so much sediment that terraces are built continuously. So I'm going to leave you with a question, not the regular question which we generally ask, what controls sediment generation and sediment accumulation, but here in the northeast Negev, where sediment apparently is abundant, transport capacity has no limit. What causes the breaks in sedimentation? There's so much sediment. What causes the breaks which enable the incision, which actually control the overall long-term landscape development? Thank you.
The next stop, the last before the coffee break and other things, is by Ginat. Surface properties influence on racial runoff in hyper-arid areas. I think this is not
So from stream capturing, accumulation, incision, we're coming to the recent and talk, and we will talk in Iran about the factors affecting Iranian runoff relations in extreme arid desert, extreme arid desert in natural conditions. I'll take 2 minutes in Hebrew for Aaron and for the history of this research. What I mean, Aaron was my supervisor, ל-PhD, ומהדוקטורט התקדמנו למחקרים, למחשבות, ואהרון אומר לי כמה שנים, תשמע, חייבים לחקור את אפקטיביות הגשם שיש במדבר, הצפח קיצון במרחב היפה, המגוון כל כך, של תמנה, של גרופית, עם מכלול של יחידות צאלה, ואני אומר, אהרון, עזוב, אין גשם. מ-95 עד 2009, אולי היה אירוע גשם אחד גדול בנחל יעל, אבל כמעט ולא היה גשם, והאהרון מתעקש, ואנחנו מדברים ואומר, תראה, אם נתחיל את המחקר, יתחיל לרדת גשם. מהאירוע, בצדק, מהאירוע היסטורי של ה-18 באוקטובר בינואר 2010, ועד לפני 3 שבועות, 28 אירועי גשם, אומרים שאולי אנחנו עוברים לאזור הטרופי, אולי לא, אבל 28 אירועי גשם שבחלקם הגדול אנחנו נציג במחקר מדדנו וראינו, וכך זכינו בעצם למחקר, שאני חושב לא ב100% ייחודי, אבל למחקר של גשם אמיתי במרחב הדרומי. So the main purpose of the research to return rain and floods to the southern Arabah, as we explained, following the Ahron suggestion, to examine the diverse runoff-field on slopes as a result of the type of bedrocks, the distinction between rock and plastic slopes, divided into two groups, and the type of rains that about to fall, and different types of rains, and how they affected the runoff. So just to present the research area, we're talking here, Southern Arabah. This is the satellite of Timna Valley. Solomon Pillars are here, and this is the main site for sampling. In this region, 20 to 30 millimeters of rain. Well, depends where you calculate the average. When you calculate the average, I mean, until 2010, it fell down to 15, but then it raised up. The geology map that presents the differences between the sites, and we're talking, this is Timna Valley, this is the site of one of the tributaries of Nachal Nefushtan, Solomon Pillars, this is Mount Timna, following the map of Bait, et al. Of the Geological Survey, and the other side that we choose because we couldn't have limestone here, otherwise we have to climb to the cliff near Mount Berech, so we choose the site not far from the road, the Arava Road, near Kibbutz Borfit. This is Chatzera Formation, and it gives us the option to research to the research area, and we can see here, this is Timna Park, just to present the different landscape, the types of rocks, steep granite slopes with dikes, sandstone cliffs from Solomon Pillars Formation, with very surprising results, sandstone from Shchoret Formation, they are all exposed in Timna, and the graphite area here, as I said, beside the Arava Road on a hill slope. I want to invite Aaron. I'm reading his master thesis following this research with Aaron and me.
So first, it's an honor to be one of your students, Aaron, like many others here.
When Aaron said to Siba, I think, well, Hanan is my son and here is my grandson, following the research.
So just to Okay, just to show you that recently we got some rain. So this is from last month. 20 something millimeters, 25, 26 millimeters. But most of them in like 2 hours. Waterfall in
המפל של נחל פתורה.
עבודה השנייה.
6 בערב ולמחרת ב-12 בצהריים.
you see the lightning during the So previous works, as many of you know, were in Nachal Yael and other places, and except of the work of Aaron and Micha Klein, that got 3 rain events, if I'm right. All of the other works use the artificial rain machine to get data. So we were lucky because of the research that started. And we get some rain. How we know? The basic of our research was the plots. It's a metal frame. We collect the runoff through a jerry can. Yeah, through a jerry can. And we have a rain gauge next to each plot. And we got, as you see here, it's a list of the plots. We have 12 plots. 10 of them between 2.5 square meter to 5 square meter, and 2 bigger, 8 times bigger, just to see the differences. And we got many rain events, about 20 in most of them. This is just to show the difference between big plot and small plot next to it, just right next to each other. So what we look for in the rock plots, we just have the petrographic definition of the rocks, and we also did the LiDAR measurements of the roughness. We will explain later. In the clastic plots, we also look on the rock fragments, the rocks cover percentage, the grain size, granulometric, the volume of gravel and fine materials, and also we did this roughness with the LiDAR. This is the LiDAR, in the left it's the 2 pictures from 2 different plots. One is a sandstone, and this is a colluvial slope next to the sandstone. And what we can get from it, we can have a rasteric map that each cell have data, so we can really get numbers of roughness, or like really data of the roughness of the terrain and slope. We only picture 7 plots, but we have some information about it. We also had the rain gauge and rain intensity gauge. Intensity. We use it to know, because there is a lot of variety in rain characteristics. So the results we have first, we have a physical definition of the plot itself. This is just example from a granite colluvium plot. What's important here is we got 4 different measurements of roughness from the LiDAR. We focus only in the first one, it's the standard deviation of the height of the cell, of each cell in the map, in the plot itself. And we saw it in the literature as like a measurement that is common in the literature. Then we have the rain, different rains, and how it affects in different plots. So here we have all the plots. Each color represents different rain. The red one is the rain that caused the flood, only 7 millimeters, but in 23 minutes. And it caused a small, nice flood in Timna. And as you see, in the middle is the line. What right from the line is the bedrock plot, and left of the line is the plastic plots. And you see that in a flood event, the plots, all of them, has a lot of runoff. Okay, this is the rain efficiency. It's mean the amount of the percentage of runoff from the rain. Okay, so we see it's really high. And in other rains, for example, this was 14 millimeters, but during 24 hours, 22 hours, we see that there is a difference from rock plots to plastic plots. And a small, really small rain with only 4 millimeters, the classic rock almost didn't get any runoff. What we can say from the result on the plots, that one plot, we didn't get any runoff at all in every event, and the only 5 to 40%, depending on the plot, created 5 to 40% of the rain created a runoff, and the threshold for runoff is between 1 to 5 millimeters, depends on the plot itself. And we found a good correlation between if we got runoff in the plastic plots, we got flow in the stream below. And on the rock plots, two of them get in almost every rain, we get the runoff. Even if it was 1 millimeter of rain, we got a certain amount of runoff. But the granite, we got only 52% of the rain. We'll soon explain why. And also, the threshold is much lower, 1 to 2 millimeter. But on floods event, on floods event, we saw that similarity between the plastic, as we saw before, between the plastic and the rock plots. Why we saw differences between the limestone and the sandstone and the granite, we think that there is difference in roughnesses, okay? This is the granite plot, and this is the sandstone plot. And you see the number that you get to the roughnesses. Here it's the roughness. Here it's 6.29 centimeters, the standard deviation, and here it's 2.73. And here we get 100% of the rain cause runoff, and here only 52. So we conclude that in roughness, how it affects. In the rock plots, the more roughness we have, the less runoff we have, and in the plastic plots, the more roughness we have, the more runoff we have. Why? Because it's maybe affected from the rocks itself. The rock itself on the plot, on the fine material, create more runoff, as from this article by Kozman and Lavi from '94, and it generates the runoff inside the fine grain, to the fine grain. Okay. In one plot, this plot, we didn't get any runoff. What's different from other plots is that the slope is really high, 27.5 degrees. We thought that maybe we got infiltration because of the non-unified material, because of the slope. This is our suggest. And only you see it here. Also, you see it here after a flood took the jerry can. So maybe it did have some result. The flood took it. Our conclusion from this project. First, there is differences between the plots, between different kind of rocks, different kind of roughness in plots, and between rocks and plastic plots. And with the heavy rains, with high intensity rains, plots, rocks and plastics behave kind of similar. And the differences maybe it's because of roughnesses, but what also we realize that the major effect here is the rain. If you have strong rain, all of the plots have kind of similarity, and this is the most important thing for floods, okay? Not for runoff. We try to do some application with it. We map smaller drainage, like 300,000 square meters in Timna. We mapped it according to the similarity to the plots. We try to see if all the drainage will behave like the plots, how much excess rain we'll have, and then compare it to the actual flow that we measure in the stream. It's similar to what Noam Greenberg did in Yair. And we realized that we took here 4 events. One is from Greenbaum from his work. We took the intensity of the rain because we thought that this is the most important thing. And we saw that if the intensity of the rain increased, the losses between the plots to 5 times bigger in scale, bigger area is decreased. Okay, so if the intensity is low, we have a lot of transmission loss on the slopes, and if it's the higher it is, the lower the losses. Okay, that's it.
ticket. Okay, I brought a newspaper. Piece of newspaper from Ma'ariv, 1963, and it says, it speaks about what is inside the devil's pit in the Galil. Speaking about one of the first expeditions to try to find out this what used to be a deepest place, deepest cave in Israel, nobody came out from this cave earlier. We said that the army got organized and then they were afraid, so they lowered down a dog the size of a human being, and then there was a very brave, naturally, army officer, and the first citizen who agreed to go down to this pit was an assistant of Shatner named Aaron Ya'ir, 54 years ago. And he came out, as we see, but he lost a very good speleologist as he went down to the Negev and to observe his processes, and we are going also after him to the Negev and to see what is underground this region. Usually deserts, which cover a large part of the world, are considered not to support a lot of karst features. It is supposed generally that denization is proportional to effective precipitation and to CO2 partial pressure, which is associated with biological influence within the soil. So both effective precipitation and biology is very scarce in the desert, so there should be no karst. But when we look at the caves, I plotted them according to length and to annual precipitation. We see that most long caves in Israel are in the desert and in the semi-arid zone, right here, including some which are several kilometers long, and not in the north humid part of the Galilee, which also have more pure limestones, rather than the material in the Negev. The rocks of the Negev are richer in clastics like clay and sand, so they are less susceptible to calcification generally. So what is going on here? Here we see the plans of the largest limestone caves in Israel in the arid zone, and we want to understand what happens here, what is the reason that we find these ones in the desert and not in the Mediterranean zone usually. I'm showing a preliminary study. Here are the profile, vertical sections of the same arid and semi-arid caves. We see that they are going in the various gradients, and they have a lot of rising shafts which have cupolas at the top, which indicate rising water. In the Negev, we see that most of the caves are associated with major tectonic lines. That's the central Negev, and we see some caves that we shall talk about. We don't see all of them. The largest cave in the Negev is here, the back cave, the cave Shel Ramon, and Eshkolot cave, which is on the main road, so it's well known. That's caves in the Shel Ramon area, of course, in the limestone. It's just above the Ramon fault. And some of these caves probably were not visited by people since the Bronze Age, because we found this large thing inside and no one touched it before us. Marzeva cave is the largest, as I said, and as the other caves, has got in the plan view form of a maze, multi channels that are sub-parallel to each other, but also in vertical directions, and profiles again have several diversions upward, and we see generally quite a circular cross-section of the passages, very smooth, indicating a full pipe flow. The caves, all these caves were formed by water which filled the caves to the top, so it was under the water table, and a lot of cupularized solution pockets which indicate some convection currents within the caves. And we see some flow cutting across faults like this one, and flowing along faults, and a lot of rising chimneys or domes going up towards somewhere up. Usually they don't have an outlet at the top, and we find several caves, well-preserved gypsum deposits covering the walls and the top and the bottom of the caves on all sides, like in Canaan cave, where it's well-preserved, and in Marzeva cave, you can see the gypsum on the walls. Looking at the delta S34 of the gypsum might let some indication of the source of the sulfur in this system. And we see that usually in most gypsum deposits in Israel and abroad, actually, we find delta S34, which is positive between about 13 and 28. In Israel, it goes from the Triassic gypsum right to the Dead Sea, Holocene gypsum, and many others on the way. But in several cases, we have depleted sulfur, which is around zero, and this tells us a story of some reduction in the process, reduction associated with bacteria, and it's generally believed that the process indicates the involvement of sulfuric acid within the cave formation system, and the sulfuric acid is formed by oxygenation of H2S, and these sulfides come from depths with the water, and they probably originated by reduction, as we said, bacterial reduction of sulfides, maybe the large sulfide deposits of the Mukhila formation from the Triassic. And then this sulfuric acid attacks the limestone right here, and it makes the cave on one hand by dissolution, and deposits gypsum again at the walls of the cave. So this is the most accepted kind of cave formation process, which is indicated by depleted gypsum deposits in a limestone cave. I remind you that the caves are all in limestone. Maybe I didn't say they are all in limestone, mainly in the upper part of Judea group, in the Shifta formation. We also find within these caves some calcite spar deposits like these crystals, and also these deposits are covering some walls of some caves, such as the Eshkolot cave, and these are phreatic deposits, meaning that they were deposited from the water which filled the caves at some point. The water became less aggressive and oversaturated, and then it deposited calcite within the cave. So we can look at the isotopic signature of these deposits, calcite deposits, and we look here at the delta O18. Within the caves, we generally have Veddos Filiocems, which were studied by Anton Bax before, and here we are looking at phreatic deposits, which are generally more depleted in oxygen than the Veddos ones, and they are also more depleted towards the south. Towards the south, we are going to the left to depleted values, and they are also depleted in time, probably. This is known from lake deposits on which Hanan Ginat and Nicole Calvo have worked, and they are illustrated here. As we go back to the Pleistocene to the Miocene, we see more depleted values of the lake deposits. So the phreatic deposits are not dated yet. Maybe a few days from now we should see some dates. But in general, we see that we have depleted values in the south and more back in time. So it indicates something about the source of these phreatic deposits. Let's go to Asherim Cave, and I'll show you two maps of the region in the northwestern Negev that's the entrance to the cave. And these are Veddos Filiocems, which Anton dated down to the Pliocene, started depositing in the Pliocene into the Pleistocene. And that's the plan and the section, which is a three-dimensional maze system. And again, we see the morphology of domes and flowing full pipe water, and also roots of water flow in the ceiling. And if we look at the map of groundwater, present groundwater, within the area of Asherim Cave here, we see that the groundwater within the Judea group, there is the regional water of the Judea aquifer right in the Tel Shokit area, but in the Nitzana one well, closer to Sinai border, we see water which is chemically indicative of the deeper sandstone, Libyan sandstone aquifer. And this water was rising to the Judea group, probably, and from here there is the water is mixing with the Judea group water. We see it in several other wells. And in the Asherim Cave region, we have about 75% of the deeper water and about 25% of the Judea aquifer water. So there is some mixing, a mixing of two kinds of saturated water, saturated with respect to calcite, means that we have aggressivity, which is the aggressiveness is rising when we mix two types of water. So this can give another kind of process, chemical process, which can make caves. We look at the Asherim caves as in its relevance to the structure here. We are within the structure of the Syrian Ark, and it's a structural map. And we should look at this section. And the section shows us that we have, of course, the small anticlines of the northern Negev, and they are believed to be underlain by reverse faults like this. And the flow of water, the deep water from the sandstone reaching the Judea group in this region indicates that there is some rising of water probably along these faults, because there are a lot of aqueducts on the way with low permeability, so the fractures and the faults can supply root for the water. And we can check it also in the northeastern Negev, where we see the caves indicated by this kind of circles. According to the size, bigger circles indicate larger caves. We see that the larger caves are oriented along a tectonic line. Actually, here the tectonic line is very clear because it's a reflection, it's a monocline of the solar anticline. But here there is not much surface indication of this tectonic line, but we can extend it along this green line because of the line of caves. And we suggest that the water is associated, the water which made the caves is associated with these tectonic lines. Looking at one of these caves, the Tzavoa cave, which is within the Zohar anticline, it's a good place to check the hydrogeology, the old hydrogeology, because we have several wells which were drilled to find hydrocarbons, mainly gas. The Zohar 7 well, for instance, crossed 2 times this aqueduct, the Jurassic aqueduct, and it means that we have a reverse fault right here, and the fault is underlying the cave again. So we suggest again that there was some rising of deep waters through this fault. The caves are hanging up in the Dead Sea fault, the normal faults of the Dead Sea rift or transform. Some of them along the Dead Sea are half a kilometer high above the Dead Sea of today. And our research hypothesis is that the caves really predate the Dead Sea transform, and before the Dead Sea transform started to evolve, we could have a lot of water, deep water flowing in the Nubian sandstone deep, rising along the Syrian arc and the Negev structures to the south, which served as a kind of preferable area to rise in. And in this map by Zohar Kurtzman, we can see that during the Oligocene and maybe after the early Miocene, we had only this part of Israel above sea level. So this might explain why we have caves mainly in the desert of the Negev and Judea. And looking for the catchment of this water, we're going here after the Yoav Avni and others who speak about the major truncation surface, which was along the present Red Sea, and we had a huge area of sandstone exposures here, and we heard from Tamir Brodik today how sand is a very good material for infiltration and recharge of the groundwater. So looking at this area, which is around 400,000 square kilometers, it's a huge area. You can see this section where the water could infiltrate along these Paleozoic and up to Mesozoic layers and go up again in this huge silk line rising to the Negev and Syrian arc region, and a small section showing the same thing in Sinai shows that we have water coming from the basement, flowing into the sandstone where there must be a lot of infiltration, and then going into the deep aquifer. So I will go over the conclusions because of lack of time, and say thanks to several people written here.
The next topic about moving recent advances in the study of the Negev Bless.
Everybody. So I'll start with this slide. When I started my PhD around 2004, my advisor gave me really good advice. They told me, go learn something from Aaron Ya'ir, and I went and searched for a course that he gave and found this field course in geomorphology. It was a great experience. At the beginning, he took us to his field station, and we strolled with the hammer and checked all the stuff. But eventually, we found ourselves inducing a runoff and soil erosion in the Negev Bless. This experience helped me later on with my PhD. Thanks, Aaron. Okay, so the recent advances in the study of the lakes are focused on the change from lake Pleistocene dust sink to Anthropocene dust source. So what we actually see with the lakes, as Kiki told us, it's a late Pleistocene feature, but now it's a dust source rather than a dust sink. And he studies with Ya'ir from the geography department and with So we are focusing on the dust cycle that we all know, and dust affects the climate and the biochemistry, the ocean biochemistry, and the land and the forest, etc., etc. I will not go into this, but the main thing is that we lack information about the dust sources. Even though we have remote sensing observations and modeling, etc., we don't have enough information about sources, and this is part of the focus of this research. And when we talk about the dust storm, we can divide the dust storm by their spatial scales. With the synoptic scale, one of the thousands of kilometers, are the major and most significant dust storm. This is what is estimated today. But there are also the mesoscale storms that are a few hundreds of kilometers, a few tens of kilometers in scale, such as the convective systems as Habubs, that I will show in a minute. Habub is well known from southwest US, from Africa, from Arabia, and it is not well known in Israel, and I will show this example here. And we still don't know the role of these Habubs, of these convective storms. Are they important to the global dust cycle or not? And especially when humans change the surface, maybe they increase soil erosion by wind, as we see here. So, what is a Habub? Habub is a word in Arabic that means strong wind. And at the beginning of their research, it was termed, like every dust storm was termed as a Habub. But later on, the terminology changes, and now Habub means the downdraft of thunderstorms that create this really impressive wall of dust, like you see here over Phoenix, Arizona. And so the main mechanism, or the well-known mechanism for the Habubs until now, people are talking about the downdraft from a convective system, from like thunderstorms, but as we will show here, we propose a different mechanism for the formation of the Habub in Israel and in other places. So a bit of dust in Israel. So as I said before, that most storms are synoptic scale, the same for Israel. This study of Ya'ir, it shows the categories of dust storm according to the synoptic system, with the Cyprus law, which is responsible for most of the storms, the dust storms, and then the Sharab cyclone, etc., etc. And you see the work of Calderon also. She did back trajectories of dust storms, and also she divided them according to the synoptic system. So we have the cold depression, the Red Sea, the Sharab, and so forth. So according to this scheme, most people think that most of the dust sources, most of the dust that reaches Israel originate from outside of Israel. So it's from distal sources, for example, from the Sahara or from Arabia. And there is not much information about dust sources in Israel. There are some studies that try to estimate the potential of dust emission from sources in the Negev, such as the work of Gerson and Kiki, and a more recent work by Lincoln, and also a research group in Beersheba nowadays from the geography department that study agriculture field, the dust emission from agriculture field, and I will go back to it in a minute. And also there is not much information about mesoscale system in Israel, although there is one paper by Ofer Gossens that suggested that there is a habub in Israel, but we don't provide any documentation for it, and I will show you. Okay, so the motivation for the study came from this image that was published in Ynet, the Israeli internet newspaper, and actually this also, there is a birthday for this dust storm, actually 10 years ago this dust storm occurred, and this is a habub, okay? As you can see, you have this impressive wall of dust, the height is 1 kilometer, and these photos were taken by a chopper pilot, helicopter pilot, and I talked with this pilot, and at the beginning he flew right in front of the storm, and then he went up because he didn't, of course, want to hit the storm, so we estimated the height 1 kilometer, and here this is Nevatim airfield, this is the runway of Nevatim, and it will help me later on to map this lineament, the wall of dust here. So the goals were to investigate the dynamics of this storm, the 2nd of May 2007, and to identify the dust storms, which we read about in the 7th of May. So a bit of background, so we're talking about the less. The Nevatim airfield is just east of Beersheba, so the photos we're taking here. So we are in the heart of the less region, and it's a lake plasticity feature, as I said. The natural surfaces are crusted, like almost everywhere in the world, but when you disturb the surface, of course, you expose the sealed grains to be eroded either by wind or by water, but here we're talking about wind, and this is very important, and we'll go back to it later on. So we'll start with a synoptic overview. This is the mean sea level pressure, and this is Beersheba, the place nearby where the photo were taken. And this is the time of the habub, the 2nd of May, 12 UTC. So this is 12 hours before. This is the cold depression, which is located in Libya, near the border with Egypt. And we see it's far away, more than 1,000 kilometers from Beersheba. 12 hours later, this is the time of the habub that hits Beersheba. We see that the low is still about 100 kilometers far away from the habub. And if you know how to, if one of you, like Ridayan and know how to read these synoptics map, then you can understand that this low cannot explain the high-speed winds that hit Israel this time, and we should expect weak easterly winds according to this synoptic condition. And 12 hours later on, the low advances toward Israel, and only 24 hours later than the habub, we see that the low is situated over Israel, and indeed this low brought dust, but this time this dust is a Saharan dust. Okay, so we have here two distinct features. Habub, which is a local storm, it cannot be related to the synoptic scale, so the dust must origin from the Negev. And on the other hand, 24 hours later, we have the regional, more popular storm that originated from the Sahara. So at this time, the dust from the Sahara was here, not here. So show it with these photos, these modest photos. So this is a few hours before the dust, the habub is here. And we see the low here, and this is the dust that is related to the low still over Egypt and Libya. And 24 hours later on, this is the original dust storm. Now the low is situated over Israel, and this is the original storm that was brought by this low and from the Sahara. Okay, so let's look at the temperature and relative humidity in Beersheba. This is the time. This is 2nd of May, 12. This is the Habub time, and this is the original Sahara storm 24 hours later. This is the temperature and relative humidity. We see that the gradual increase in temperature, so the heat is going up to 35 degrees right before the Habub, and we see the relative humidity go down to 5% humidity just before the Habub, and we see that the Habub hit Beersheba. During this time, we see abrupt drop in temperature, about 10 degrees drop in temperature, really abrupt, an increase in humidity, which means that we have moist and cool air that is related to this Habub. And we'll go back to it in a minute. And we see that a few hours later, the temperature go up again and the humidity decrease again. So it's a very short feature. And this is the wind data. This again, time, wind speed, wind direction. The average wind speed 10 minutes is in blue, and gust is in red, and the circles on the wind direction. And this is what I told you before from the synoptic. You can assume that you will have weak easterly winds, and this is what we see here. So the direction is east, and the weak means that it's the wind speed is below 5 meters per second. And then we see during the time of the Habub, we see abrupt increase in wind speed and also change in wind direction. So now the direction is from the northwest. This is really important. So we see that the Habub or the wind came from the northwest, and it reaches the average wind speed over 10 meters per second, and the gust, which is maximum speed, wind speed within this 10 minutes interval, is over 20 meters per second. And also, we see again that its feature is a short, has short life, so the winds are going down a few hours later, and we go back to this synoptic scale winds, which are easterly and weak. And only 24 hours later, we see the effect of the original Sahara storm. The winds are a bit higher, and the wind direction changes also. But again, this is a different feature. So here I present time contours of the maximum wind from every station, and this can show you the advancement of wind from the sea inland, which actually means that we're talking about sea breeze. Okay? We think that the wind that was responsible for this Habub is related to sea breeze, and we see the front of the sea breeze advanced inland is very similar to other studies that they worked on the sea breeze, and these are the lineaments, as I map them, of the wall of the dust in Nevatim, east of Beersheba. And we think that because of the temperature differences between the hot and dry air and the moist and cool air of the breeze, so actually the sea breeze acted as a gravity current or a density current. And this caused the high-speed winds by the sea breeze. Okay, what about the dust? So here I show a PM10. PM10 is the concentration of dust which is smaller than 10 micrometer. This is time, again, this is the Habub, and this is the original Sahara storm. We have only one station from Beersheba, and we see the abrupt increase and decrease in dust concentration. This is 3-hour average, so I guess if we had more, if the interval was shorter, then we can see even abrupt picture. And we see nothing up north. In the center of Israel and in the Galilee, we see maybe a bit in the Shemesh, but everything is background levels. And we see again the Habub is over, everything returns to normal, even in Beersheba. and we see how the original Saharan storm is different here. The entire land of Israel is affected by the original Saharan storm, even in the Galilee, center of Israel, and the southern Israel. So again, this is a different creature. So about the dust sources, perhaps this is the big story. So we said that the wind came by the sea breeze, so it came from the northwest, and this is Nevatim, these are the photos, and we have dust data from Beersheba and from Hatzerim. So we had the Habub also here, so we should look for the source upwind of the dust where we measured it, and if I look upwind, I see the less, all these colors are the less deposits, and here are some sand dunes. And we see that it's not only less, we have here the agricultural field, these are the rain-fed wheat field, which everyone knows from the northwestern Negev. And these are the wheat that's collected during this season, April and May. And we know that most of these fields are used for livestock grazing. So if we have the agricultural practice and we're grazing, so of course we break the crust and we make the seal grains available for wind erosion. And there is a nice paper by Chandler from the group in Beersheba, where she measured the dust potential using wind tunnel from this area, so from a control point and from agricultural practice and from grazing, and found that agricultural practice, the dust potential is 6 times more, and the grazing is 17 times more. So it reinforced our assumptions that if we break the crust, the seals are available for wind erosion. And this is how the area looks like if no one visited Northern Negev. And here we can see, again, the NDVI that was shown before, how the NDVI, which represent the coverage of vegetation, the ground coverage of vegetation, from high values before the Habub is here. This is beginning of May. So February, March, we have high NDVI values inside these agricultural fields, and it drops down during March and April, and during the time of the Habub, we see that the area is completely dry, as the area of the control point that I took here, this line here, which is outside of the agricultural field. So, to summarize, we see that the sink of dust, the Lake Tosius sink, is actually now, because of human practice, becomes a dust source. And this is really important because what we see here is less recycling. This is important if someone is collecting dust samples nowadays and trying to say something about the Sahara as a proxy, then there might be a problem here because maybe the dust that one collects now from Israel is not related, or partly is not related to the Sahara, but it's recycling of paleo dust deposits, lake places and dust. So, to summarize, we document for the first time the occurrence of Habub in Israel. The Habub was generated by a sea breeze and not by a convective storm. The dust sources were the loessile soils that were disturbed by agricultural practice and grazing. And we emphasize the local sources of the Negev, which were neglected in the and we emphasize, again, the less recycling as an important process. We think it's important also in other places in the world and not only in Israel. Thank you.
Sheila, question? One? Ken? The big dust storm came from Syria and was attributed to neglecting of the agricultural filter. Do you have any conclusions about this?
And there were several papers that appeared. Danny maybe worked on it, maybe he can say about it. Yeah, people are talking about the drought. That we had a lot of rains during the 10 years before. And other people talk about the, when we describe the surface, about Daesh, ISIS, etc. But I don't know if there's a clear conclusion. Maybe Uli or Danny know more.
ask Danny later. Okay, and the last one today. עיון, determining water velocity and discharge even in large floods.
I was recently in Missoula. I wasn't there when the flood was there, but each one of us would have liked to be there. We come after floods, and then we try to understand what happened after the flood. Or we stand beside the flood and say, oh, gee, this is really nice, we take photographs. There are a variety of methods that are available today in order to determine what happens in a flood during the flood. There are some very modern instruments. The U.S. Geological Survey, for instance, and all hydrological surveys in modern countries, except Israel, use ADCPs for depth of flow of about 1 meter and up to about 4 meters per second. An ADCP is about $10,000. You don't put it in velocities that are above that. So how do you measure velocity? You put a current meter in? You put a graduate student in? But we still want to know how much water is there. Not just calculate it, not knowing what it is. Now, geosciences are an empirical science. So is hydrology. Hydrology, unlike, for instance, geomorphology, has been losing a lot of field-related measurements. In fact, in the last 2 years, Water Resources Research has had several papers that delineate the downfall, or if you wish, the decrease in field-related methods in hydrology. We geomorphologists need hydrology just like we need sedimentology, tectonics, and so on. So I'll talk today about geomorphic-related hydrology in floods. Louis Dayan is here. 1968. You were talking French more than you do. You were giving us the introduction to geomorphology. Thank you. So during about 5 years until last year, 3 groups were looking into the option of determining water discharge during floods, during those conditions where you can't get in with regular equipment. Now, a variety of equipment has been around for some time. The Japanese, for instance, have been using radar for about 35 years. At the time, one radar cost about $15,000. Japanese put on their large rivers that are very steep, 5 of them. Who else except the Japanese can put that much equipment into one river that flows every year at very fast velocities? And there are other rivers that flow very fast during floods, but we wouldn't want to use that money. The assumption of the Japanese in the 1980s was that if you measure the water velocity, you know what the average velocity is. But that was an assumption. And although there were some hydraulic measurements in labs to determine whether that assumption is more or less correct, we wanted to know to what extent can we determine the average velocity during a flood from surface velocity measurements. Guido Zaleski and the group in Trento are hydraulic engineers geared toward geosciences. And Jérôme Decaux in Ilstin in Lyon is probably the leading European hydrologist interested in hydrology. So all of us together with the students, Daniel and Fabio, were looking into different conditions and trying to determine under field conditions to what extent can we determine average velocity from surface velocity. We wanted to do that in large floods, or at least also under flood conditions. This is an example of a flood. Noam Greenbaum is here. He looked at that flood. This flood in Nachal Tzidon, 2004 had a return period of about 120 years. I had some graduate students put scour chains in here, but they weren't during the flood itself. Nobody puts any instruments in that. So we have to use some remote sensing methods. And there are several of them, and I will mention especially one today. If the flow velocity is such that the velocity distribution is logarithmic, we can define what is the relationship between the surface velocity and the average velocity. And this definition is something we'll call alpha, the ratio between the average velocity and the surface velocity. And if the ratio of the roughness relative to the depth is such that it's anywhere between thousandths to a hundredth, then that ratio can be shown to vary only about between 0.85 and 0.9, and not more, if the flow is fully turbulent and if the velocity distribution is logarithmic. Now there are conditions where that is not so. If you go into a curve of a bend, if you go into a canyon where there are big boulders, you have to know where to measure. But if the velocity distribution, that is so. And if the roughness is even larger, and if it's only about 1/10 of the flow, still the ratio is in a very narrow band. So if we go to flow conditions that are relatively deep, relatively fast, where the roughness is relatively small, we measure the surface velocity, we should be able to know what the average velocity is. And we can't do that in very shallow flows. So this is the velocity distribution that we would expect to have in any condition where it is logarithmic, and we'd like to know how alpha varies. I'll be talking about alpha as we use it in radar. There's a second method. Some of you may go to a conference that will be held next year, in Akko, next week in Akko, and there one of the students will be talking about a second method called large-scale particle image velocimetry, yet not used in Israel, not yet used in the United States, but used a lot in France and some other countries, where it is possible to find out not only the average velocity, but the vectors of velocity in the flow. And what is important about that second method, which I won't delineate here, is that the flow that we think is in the downstream direction is not. The flow in every river, even if it's totally straight, has a secondary flow. And that secondary flow can also be seen on the surface of the river. And from the large-scale particle image velocimetry, we can determine two things. We can determine the depth of the flow, and we can also determine the average shear of the flow without touching the flow. The average for size. So this is really something very new that just came out in the last 2 years, and it's very exciting. I'll be talking about the other type of system, and that is the one that's based on radar. So, surface velocity is something that has been around for about 25 years. Essentially, it uses a Doppler effect, and if we know what the velocity is of the flow, we'll be able to translate that to a different kind of a frequency. That frequency is measured by an instrument, usually by an instrument that is located in one place on a bridge. The advantage of having it portable is that you can move from one flood to another when it occurs. And as we know, floods don't come often, but when they do, they're in a given area, and that's where we want to go and measure them in different locations. So the Doppler shift allows us to determine the velocity of the flow within given limits. The limits are about 0.3 meters per second. Less than that, it won't work. Noise here. On the lower Jordan River, it won't work. Hardly moves. But it goes up to about 9 meters per second. And there aren't many flows that are above that. And it's very well documented in laboratory. Not only that, the accuracy is very high because it uses a very high frequency. So what we need to know are only two things: the tilt of the instrument, and that is done automatically by the instrument itself, and the angle relative to the flow, which is called a yaw. If you have a boat, you know what a yaw is. So you can determine the velocity either if you stand on the back or if you're on a bridge. You don't have to be on a bridge in order to use this instrument. We use it in several different locations. In the semi-arid area, in a location where we could enter the flow and actually gauge it using an electromagnetic current meter. And here is the instrument itself, the portable instrument. Or during flood events where we put an instrument into the flow and we did not get into it. We also use it in very shallow flows. This is near the Dead Sea. This is about 20 centimeters deep. And one would think from what I said originally that for such flows it won't work. The roughness here is about half a centimeter. And it worked also here. We use it in the Tagliamento River, the only large braided river in Europe, which is still very wild and very natural. It's located near the Adriatic Sea, and we use it in 3 different locations, where each one of the ana branches was deep, in places where the ana branches were more shallow, and in places where they were very shallow. In addition to that, we measured it in the 2nd largest river in Italy. Somebody mentioned what you were drinking, Aaron. They have good wine here. So this is the Adige near Trento, very large river. And we also measured further upstream near Bolzano at these 2 locations. So we measured large rivers, small rivers, and we measured them from a bridge and also from a bank. And we measured them also in a wild alpine river, the one that I showed you at the beginning, the Arc and Moyenne. Rivers like the Arc have served geomorphologists for many purposes. We generated floods because the French, like the Swiss, the Germans, like the Italians, and like the Austrians, they generate floods every year in order to desilt their reservoirs. If you know in advance when they're going to open up the gates and what the discharge is going to be, you could be out there and take many measurements. There were 20 of us there, twice, one night, 1 year, and then another year. So there were quite very nice measurements taken also on this place. And this is the river where we took the measurements, also with high concentrations, suspended sediment, using both current meters and ADCPs. So we're going to compare data from these just to see how well this method does. The instrument itself shines on the water itself, and the height above the water determines actually the size of the area that is being shown or that is being measured. So we have to determine, are we going to be measuring only part of the river? No, we want to measure the whole cross-section of the river. So we have to move from one place to the other at all these locations, and that takes time. Not too much. For a big flood, it might take 20 minutes, 30 minutes, depending. We can also shoot far away and take just 1 or 2 measurements. And we want to see what the effect of that is, because if we can take measurements very fast while the flood occurs, or run to another river and take several measurements, that would be very useful. This is being done today in France and in Italy by the hydrological services. So let's look at some of the results. One of the results of this one, this is how the velocity coefficient, the alpha, varies with the local relative roughness. And as we said before, when the relative roughness is large, the scatter is large. We can't use this data because there's turbulence, there are big boulders, there are a variety of flow that are not standard log flow. And therefore, we can't use it in those instances. And if we look now at depth of flow, and how alpha varies with depth, it's the same thing. When the flow is very shallow, in this case, for all those rivers that I mentioned now, about ½ a meter, there's a lot of scatter. Once it's above that, it tends to show very good results. So the alpha is within a very narrow range. And once we don't take each one of the single measurements, but we take the average of the measurements for one given cross-section, then for that global relative roughness, we get very narrow band of alpha values. What that means is that under those conditions, and they're good, especially under flood conditions, we can take a few measurements and determine what the average velocity is, which is what all of us really want during a big flood, in addition to knowing other things about the flood. Now we'd like to know that in order to know what the water discharge is. So here we have a situation on the Adige River, and the highest discharges where the ADCP could be used were about 500 cubic meters per second. So it's not as high as in Brazil. Once we used the radar, we could go up much further, and in the meantime, measurements have been made up to almost 1,000 meters per second. So we can use that in order to alert hydraulic engineers and also geologists to conditions of floods that we've not been able to measure in Suriname. So computing discharge at high flow is possible today. It is relatively cheap. It's relatively fast. It took me 10 minutes to show a hydraulic engineer in France how to use the instrument. Then I let him make the measurements. And we compared that to mine and to the ABCP. They were almost the same. Here we see what the relative distance is, or how good are the rating curves when we use this technique under very low flow, when the roughness is high. And here you see that it's not very good. But once we go into higher discharges, whether we have 13 different points, or whether we lower it to half as much or a quarter, we still have very good estimates of the actual discharge at that location. So what it means is that here we have a method that can allow us under field conditions for personnel who are not very trained to be able to determine those conditions that are interesting, that generate movement in rivers, that move sediment, and so on. This is the situation that we have to get away from, the very shallow situations. So the velocity estimates are relatively rapid and relatively accurate. I would like to finish here to thank Aaron for being the first really person who brought me into geomorphology in 1960. Thank you very much.
אוקיי. משהו שעות חיכה לו כל היום בסבלנות. כמה דקות יש לך?
Good afternoon, ladies and gentlemen. Thank you very much for your participation. Thank you for your participation in this special event for me. I'm really glad to see that my old students still remember, and I like that. I'm going to tell you a story. I wanted to give a talk, a PowerPoint presentation, but this man said, no way. So I'm going to tell you a story instead of a PowerPoint presentation. I was lucky to start my academic work in a period when geomorphology changed completely its way of research. Until 1960s approximately, of the last century, geomorphology was mainly structural geomorphology dealing with landscape units very close to geology. Nothing about processes. But after the 1960s, there was a drastic change, and geomorphologists became interested in Earth surface processes. And one of the indications is that approximately this time, a new journal appeared, Earth Surface Processes. Now it's called Earth Surface Processes and Landforms. Why? Because when it appears the first time, all of the old geomorphologists says, oh, what about landforms? We don't need the processes, we need the landforms. Now this transition was very important because when we talk about processes, you cannot restrict yourself to geology. You need to know about hydrology, about pedology, about zoology, about botany. So geomorphology became an interdisciplinary research. And that was very important. And in fact, this is exactly what you have seen today. Most of the talks here were about processes. And what is more important for me, more interesting, is that most of the speakers, and I thank them for that, presented works conducted in arid and semi-arid areas. Because this is where Israel can give the best, I would say, to the world. It's a small country, but with a variety of landscape, so we can deal with very different aspects and different scales. And this is what we've seen today. And I would like to thank the speakers for that. And now I'm going to tell 3 short stories. And here one. The first one, all of them, in fact, relate to arid and semi-arid areas in dealing with processes. In 1972, I established a research station at Sidi Boker. And my first observation was that we get a lot of runoff, high frequency, high runoff yields from rocky surfaces, almost nothing from the colluvial areas for very short distances. And I said, come on, what's this? And in fact, we did get more runoff from short slopes than from long slopes, because the longest slopes had a rocky surface at the top, but very long colluvium at the bottom. And then I said, well, if this is the case, we can simply say that runoff amount at the base of the slope depends very simply on the relationship between the rock area and the soil-covered area. If the rock area is very long, no colluvium, you get a lot of runoff. But if you have colluvium, the colluvium limits flow continuity down to the channel. And then I said, this idea is correct. Let's go to see what happens in an area of 200, 250 millimeters. Unlike the rocky desert in the Negev, northern area is covered with less. But the less, there's agreement, was deposited during a wet period. But the less deposited during the wet period covered rocky surfaces and covered very coarse particles in the channels. And then ask the question, how come? We have more rainfall, but less runoff. Why is it that the less covered rocky surfaces during the period of higher rainfall? Also, the effect of less deposits in the deposition had very negative effect despite the increased rainfall. Why negative effect? Because most rainstorms were low in amount and in intensity. Depth of water infiltration was limited. Because of that, we increased the salinity of the soil by rainwater and by dust coming into the area. So we moved into a humid area, but the result was a desertification effect because of the change in the ratio between rock to soil cover. This is the first story. The second story, I said, okay, I'm not going to work in rocky, sandy areas. I'm going to work in a sandy area along the Israeli-Egyptian border. You would say, you know, if you double rain amount along this border, you would expect a better water regime in the wetter area. But again, the result was exactly opposite. There was less water availability in the wetter area than in the drier area. And it's sand, nothing else. 95%, 94% sand. In this area, the sand dunes are semi-stabilized. And looking at the area very quickly so that there is a huge difference between the wet and the dry area. The wet area, where rainfall is 180 millimeters, is covered with a thick biological topsoil crust, dominated mainly by mosses that absorb a lot of water. The drier area, we do have also a crust, but it's mainly dominated by cyanobacteria. Cyanobacteria do not absorb a lot of water. So what was the result? We have more rain in the north, but the mosses can absorb all rainwater at most rainstorm. They limit the depth of water penetration. The result is drier area in the wetter area and better rain condition, better water availability in the southern area where rainfall is more limited. So again, a strange correlation between rainfall and water resources. And that's the importance, I would say, of interdisciplinary research. Very often, until say 10, 20 years ago, no one talked about the role of biological topsoil crusts. They were not considered as important when dealing with earth surface processes. The third example, and the last one, refers to two adjoining areas with the same rain amount, 280 millimeters. One is the rocky area, and one is the less covered area. The rocky area with steep slopes, steps, and below the steps adjoining to it, soil strips, wet plots 1.5 meter long, 7 meter long, 20 meter long, and we had one monitoring station at the outlet of the small drainage basin. We were lucky this year, the first year, we had an extreme event. 36 hours of rain with twice a rain intensity of 90 millimeters per hour for 1 minute to 1 minute and a half. What was the result? In the small plots, runoff coefficient, the frequency of runoff was very high, 8, 9 flow events. But runoff coefficient at the small plots were very high, between, I would say, 23 to 30%. When you move to 8 meter, it drops down to 7, 8%. And when you go to 20 meters, it drops to 1%, even in the extreme event. And the extreme event of 105 millimeters with twice very high intensity, no runoff at the outlet of the basin. So high frequency of flow events over short distances, over hill slopes. The longer the hill slopes, less runoff. You go to the outlet of the basin, 0. In an extreme event. The reason for that is the same as for the accumulation of the less. Most rains in our area are low, most rain showers are low in amount and low in duration. Like even an intensity of 1.5 millimeter per limit, it lasts a short time. Flow distances are very low, and we do not get a continuous flow. Now, when I move to the west, with the same rain amount, we have a less covered area. Slope angles are 4 to 6%. But from the hydrological point of view, a completely different hydrological regime. 4 to 8 flows in a year in ephemeral streams. When we compare it, to the rocky area, when we didn't get any runoff, we do get runoff in the less area, even when rain amount is below 5 millimeters per hour. So a very high frequency. At the same time, extremely low peak discharges. And so if we look at the peak discharge of the basin where I've been working, that covers 11 square kilometers, we do get peak flows of something like 1, maybe 2 cubic meters per second of peak flow. If we look at drainage basins with the same size, 10, 11 square kilometers, in the eastern part of Israel, along the rift down to the Dead Sea, there will be 2-3 flows a year. But peak flows can reach 100 cubic meters per second. So huge difference between the less covered area and the rocky areas. But the question, if peak discharges are very low, it probably means that you don't get any runoff from the hill slopes. And our hypothesis was, in fact, that we don't get any runoff from the hill slopes. All of the runoff comes from the channel itself. Why is it that we don't get runoff from the hill slopes? Because, again, from our data, from many data that we have in the area, the final infiltration rate for the less covered areas is 10 to 15 millimeters per hour. But very often we do get runoff with less than 5 millimeters per hour. So we have analyzed many properties about the hill slope, the chemistry of the soil along the slope, 400 meters long, particle size distribution, depth of water infiltration, no change along the slope, completely uniform. And that is an indirect indication that there is no runoff. And then I said, okay, if this is the case, we must find the reasons for the high frequency and the low magnitude of flow in the properties of the alluvium itself. So what we have done is very simple. First of all, we checked the particle size distribution in the alluvium and on the slope. In the alluvium, 40-45% of clay. Over the slopes, 27-30. We've looked at the mineralogy. In the channel, the dominant clays are smectite and delete, which are highly dispersive. We do get them on the slope, but much lower amount. Third thing, we checked the depth of water penetration in the channel and at the hill slope for an extreme event of 56 millimeters in one day. Depth of water penetration was lower in the channel than over the hill slope. You wouldn't expect this. Usually you would say, where from do we get the water from groundwater? In the channel. So our conclusion finally was the following one. Because of the high clay content in the channel, because of the mineralogical composition of the clays in the channel, what we do get very often is a sealing of the top of the alluvium. And once we get the sealing, we can get runoff at very low intensities, below 5 millimeters. And once the top 10 centimeters are sealed, at the next rainbow, we have excellent chances to get runoff. What we have also done, I forgot to tell you, that we have looked with the electron microscope at the porosity of the material in the channel. The results were really excellent. The porosity is the top centimeter, 3-4 centimeters in fact, 7 to 10%, very low. And we have no connection between different voids. So once this unit is sealed, it's in fact what we do get is an impervious layer. And on an impervious layer, you can get obviously water runoff even with a very low intensity. So I would say, what is my general conclusion from all these projects? My conclusion is something very simple. I think that the geological time scale, time has eliminated the non-important factors. And very often, you are left with 1 or 2 factors that control water availability to the water system. In the case of the sandy area, the difference is the biological topsoil crust. In the case of the less area, the difference between the composition of the topsoil in the channel and on the hillside. So very often what we do is one or two factors to control the system. And our role as geomorphologists is to detect them. And once we do that, it's very easy to understand the system. Thank you.
משוחררים.
תודה רבה לכולם.